Hello students, welcome back to next session where we are going to see specific humidity and dew point temperature. So these are the two other properties of moist air, so that we are going to discuss in detail. Already we have seen the brief introduction about these two, specific humidity as well as dew point temperature. Specific humidity, it is also known as humidity. By default it is called as humidity, and dew point temperature, uh, dpt, so that also we have discussed already. And now in detail we are going to see here in this session. These are the topics in this unit. So today we are going to see the specific humidity and dew point temperature. Psychometric properties. So dry air and water vapor form a binary mixture. So that's what we have discussed in first session itself. A mixture of two substances require three properties to completely define its thermodynamic state. So here the mixture of two substances require three properties. So three minimum properties required to completely define its thermodynamic state, unlike a pure substance which requires only two. So pure substance normally requires two properties, whereas the mixer requires three properties minimum. One of the three properties can be the composition. So composition also can be considered as one of the three properties. The properties of moist air are called psychometric properties. So psychometric properties already we discussed in first unit, its first topic itself, and the subject which deals with the behavior of moist air is known as psychrometry. So psychrometry, what is psychrometry? We have seen in earlier session also. So here the moist air, we are dealing about the moist air only. Water vapor is present in the atmosphere at a very low partial pressure. So normally water vapor is present in the atmosphere at very low partial pressure, very low pressure. At this low pressure, the atmospheric temperature, the water vapor behaves as a perfect gas. So already we have seen in earlier session. So this water vapor is considered as perfect gas only. So all perfect gas laws are applicable to moisture also, moist air. The partial pressure of dry air is also below one atmosphere. So one it is partial pressure is normally considered to be below one atmospheric pressure, which may also be considered to behave very much as perfect gas only. The Gibbs-Dalton laws of perfect gas mixers can therefore be applied to the case of the mixer. To apply to the case of mixer, in air conditioning, practices, all calculations are based on the dry air part, since the water vapor part is continuously variable. So here the all in air conditioning practice, all calculations are based on the uh, dry air part, since the water vapor part is continuously variable, it is not a constant number. So here in air conditioning, it is based on the dry air part only. For defining and calculating the relevant psychrometric properties, we may consider a certain volume V of moist air at pressure P and temperature T containing Ma. So Ma, mass of dry air. So mass of dry air is in short it is called as Ma, and Mv the moist vapor, the that is the water vapor mass, the mass of water vapor. The actual temperature T of moist air is called the dry bulb temperature. The actual temperature T of moist air is called as dry bulb temperature. So that is dBT. It is actual temperature of moist air. The total pressure P, which is equal to barometric pressure, is constant. So here you can see in this simple diagram. So dry air, the mass equal to MA kg, the specific volume is equal to VA meter cube per kg. So A is nothing but dry air, and water vapor, it is V. So mass equal to MV, specific volume is VV meter cube per kg. So the volume V is capital V is total volume, and M is total mass, and pressure is total pressure, and T, capital T, is total temperature. So here it is the mixture of dry air and water vapor. So this is known as moist air. Moist air. So first property in this topic is specific humidity, or it is also called as humidity ratio, or simply it is called as humidity. Whatever may be the name, you have to write the same answer. So specific or absolute humidity or humidity ratio or moisture content, as it is variously called. So there are so many names. So specific or absolute humidity or humidity ratio or moisture content, whatever it may be, the denoted by the symbol omega. So this is the omega is defined as the ratio of mass of water vapor. So WV is nothing but water vapor to the mass of dry air, that is dA, in a given volume of the mixer. So that is the W equal to, so that is nothing but specific or absolute humidity. So that is omega equal to MV by MA. So mass of vapor divided by mass of air, dry air. So capital V by VV divided by capital V by VA. So that is equal to VV get cancelled, VA by VV, where the subscripts A and V refer to dry air and water vapor respectively. And now the PAVA equal to R by MAT, and PVVV equal to R by MVT. So this is for dry air, and this is for vapor. Substituting for Vv and Va in equation, we obtain here omega equal to Mv rho V, that is Pv, divided by Ma Pa equal to 18.016 divided by 28.966 Pv by, so that is Mv by Ma. So that is Pv by Pa equal to 0.622 Pv by Pa. So this is the total volume, total mass of V vapor, and total mass of dry air. So specific humidity or humidity ratio, it is the units for omega kg of water vapor per kg of dry air. It is multiplied by 1000. It can be expressed as omega equal to 622 into PV by PA. So that is grams per water vapor per kg of dry air. Also, since P denotes the actual total atmospheric pressure, then from Dalton's law, P equal to PA plus PV, so that so omega equal to 0.622 into PV by P minus PV. So considering that the total atmospheric pressure remains constant at a particular locality, we see that omega equal to function of PV. So that is omega equal to function of PV. So that is the specific humidity is a function of partial pressure of water vapor only. So that is the conclusion we can make here. Accordingly, if there is no change in specific humidity or moisture content of air, the partial pressure of water vapor also does not change. It may be noted that since PV is very small and P which is barometric pressure is constant, the denominator in equations and remains more or less constant. So that is PA equal to P minus PV. So that is almost equal to P, and hence omega is approximately a linear function of PV. So that is specific humidity is the linear function of PV. The concept of specific humidity is that if we take 1 kg of dry air, so that is MA equal to 1 kg, and then the mass of water vapor associated with this dry air in the same volume is given by MV equal to omega into 1. So that itself MV equal to omega itself. So that is in terms of kg. So that the total mass of this volume of moist air is given by M equal to 1 plus omega in terms of kg, and the specific humidity is not a mass fraction of water vapor, which would have been omega divided by 1 plus omega dash, and but a ratio of mass of water vapor to that of dry air is a certain volume of the mixer. Dew point temperature. So here dew point temperature is D. So this is dew point temperature, and superheated state of water vapor in unsaturated air. So here this is the region, and this is PV, and this is D. This is dew point temperature, that is TD, and figure shows the normal thermodynamic state 1 of water vapor in moist air. The water vapor existing at temperature T of the mixer and partial pressure PV of the vapor in the mixer is normally in a superheated state. Moist air containing moisture in such a state is considered as unsaturated air. So thermodynamic state of water vapor in moist air. So this is the diagram, and illustrates the superheated state of water vapor at point 1, and dew point temperature Td is shown as the temperature where condensation begins. So the first droplet forms at this point at this temperature Td. Cooling occurs at constant pressure. So cooling is always occurs at constant pressure process only. So next psychrometric property is dew point temperature. So if a sample of such unsaturated moist air containing superheated water vapor is cooled at constant pressure, the mixer will eventually reach the saturation temperature Td of water vapor corresponding to its partial pressure Pv, at which point the first drop of dew will be formed. So that is the dew point temperature, that is known as dew point, and D in the earlier diagram, and the water vapor in the mixer will start condensing. So this temperature is known as dpt, that is dew point temperature. It is therefore the temperature to which moist air must be cooled at constant pressure, because condensation of moisture takes place. So the condensation of moisture takes place at this point, that is known as dew point temperature. So in graph we can see that is denoted as Td. So moisture can be removed from the humid air by bringing the air in contact with a cold surface or cooling coil whose temperature is below its dew point temperature. During the process of cooling, the partial pressure PV of water vapor and specific humidity omega remain constant until the vapor starts condensing. So here that is the cooling process, and it is seen that the dew point temperature can be found by knowing the steam tables, the saturation temperature Td at the partial pressure Pv of water vapor. So by through steam tables also we can find this dew point temperature. So we will see few numerical problems. So point 1, in a dew point apparatus, so dew point temperature is 12.8 degrees Celsius. So this is the point where the condensation starts, and room temperature is 21 degrees Celsius. and barometric pressure is 1.01325 bar, so that is equal to 101325 Newton per meter square. And we have to find the partial pressure of water vapor in the room air and specific humidity parts by mass of water vapor in room air. So these are the three we have to find. So first one is partial pressure of water vapor, that is PV, and at dew point temperature dpt 12.8 degrees Celsius. The partial pressure of water vapor is saturation pressure only at that temperature. So PV equal to 1.479 kilonewton per meter cube. So that is 1479 Newton per meter square. So this is the partial pressure of water vapor. So step 2, partial pressure of dry air, so that is the PA, and the total atmospheric pressure is the sum of partial pressures of dry air and water vapor. So PA equal to P total minus PV. So we know both we know here, and we can find out PA, that is 99,846 Newton per meter square. So next is specific humidity, we have to find omega. So specific humidity is defined as the mass of water vapor per unit mass of dry air. So here MV by MA, so 0.622 into PV by PA. So substituting these values, we are getting 0.009214 kg of water vapor per kg of dry air. So this is the water specific humidity, that is omega. So step 4, so parts by mass of water vapor, so that is mv by m. This is the mass of water vapor per unit mass of moist air mixer, so that is dry air plus water vapor. mv by m is equal to omega by 1 plus omega. So we know omega value we have found out, and now we can find out this ratio. So that comes as 0.00913 kg of water vapor per kg mixer. So now all this we have found out, and these are the answers. So first one is partial water pressure of water vapor PV 1479, we have found it, and partial pressure of dry air PA 99846, and specific humidity is 0.009214 kg of water vapor per kg of dry air, and parts of mass of water vapor, so that is equal to 0.00913 kg of water vapor per kg of moist air. So these are the findings from this problem. We will see one more problem. So dew point temperature is 10 degrees Celsius, atmospheric pressure is 1.01 bar, and room temperature is 25 degrees Celsius. Find partial pressure of water vapor, specific humidity, parts of mass by of water vapor. Similar problem to earlier problem. So step 1, from steam tables at 0 degrees Celsius, so PV is P sat, so that is P saturation temperature pressure. At 10 degrees Celsius it is 1.228 kPa, so 1228 Newton per meter square. So this we have to find out from steam tables. In earlier problem also we found out from steam tables only. Total pressure equal to that is given 1.01 bar. So we are converting that into Newton per meter square. So PA equal to, now we can find out. So total pressure equal to PA plus PV, and now PA can be found out from total pressure. So now this is coming as 99,772 Newton per meter square. Specific humidity also can be found out. It is 0.007658 kg of water vapor per kg of dry air. So mass fraction of water vapor, so this is also we can found out. We know specific humidity, so this comes as 0.0076 kg of water vapor per kg of moist air. And we'll see one more problem. So dew point temperature is given, that is dPT is given 15 degrees Celsius. Barometric pressure is 1.02 bar and room temperature is 28 degrees Celsius. So partial pressure of water vapor, specific humidity, mass fraction of water vapor. We have to find these three. And at 15 degrees Celsius from steam tables, PV can be found out. And this is the P total. P total can be found out. So that is 102,000 Newton per meter square. So that already given the total pressure. So PA equal to the total pressure minus partial pressure. So that is 100,295 Newton per meter square. So step 3, we can find out specific humidity 0.622. So that is into 1705 divided by the pressure PA. So PA that is 100,295. So we can find out the specific humidity 0.01058 kg of water vapor per kg of dry air. So that is the omega. Step 4, mv by mn. So that is equal to 0.01058 divided by 1.01058. So that is equal to 0.014047. 0.01047. So kg of water vapor per kg of mixture. So problem 4, very similar problem only, just to make you comfortable. I have taken up 4 problems totally. And dew point temperature is 18 degrees Celsius, atmospheric pressure is 1 bar, room temperature is 26 degrees Celsius. So partial pressure of water vapor, and we have to find specific humidity, parts of mass of water vapor. So same way at 18 from steam tables at 18 degrees Celsius, PV equal to 2064 Newton per meter square. So PA equal to 1000 minus, that is 1 lakh minus to 2000, that is 1 lakh is given atmospheric pressure minus partial pressure 2064. So we are getting 97,936 Newton per meter square, and omega is equal to 0.0131 kg of water vapor per kg of dry air. And step 4, mv by m, that is equal to 0.0131 divided by 1.0131 equal to, so that is 0.01293 kg of water vapor per kg mixer. So there ends the problems, and we have completed 2 specific humidity as well as dew point temperature, and these are the 2 what you call characteristics or properties of moist air. Already we discussed in first session, and now we have seen elaborately here in this session. Thank you, students. We will stop here, and you can refer CP Aurora book, and you can refer R.S. Kurmi and Rajput for more number of problems. So for theory, CP Aurora will be good, and please refer those 2 books. We stop here. We will meet again in next session with one more topic. Thank you, students. Thank you.